Thanks for joining my session today. The topic is Qt-Quick 3D, an introduction and best practices. Aside from this introduction I'm giving now, the whole talk will be conducted in Qt Creator. I'm going to do the whole thing live coding, show you how everything works. But first, a quick introduction. My name is Andy Nichols, and I work in Oslo, Norway for the Qt company. I work on the Qt graphics team, and I'm currently focused on Qt-Quick 3D. So, just a quick introduction of what we're going to be talking about. Qt-Quick 3D is a high-level API for integrating 3D content into applications. That's pretty much sums it up, but the best way to actually show you what Qt-Quick 3D is to literally show you how Qt-Quick 3D works, and that's what we'll be doing today. One quick note, though, is that because Qt Design Studio isn't quite ready for using Qt 6, which is what we'll be showing, I won't be showing Qt Design Studio today. I'll just be showing the QML API and the C++ API and how things work on the coding side. Hopefully in Thomas's session on Design Studio, he'll actually cover that. But that's it. Let's get started.
Okay, so let's get started. This is Qt Creator, where we'll be spending all of our time in this session today. And this is a small application that I created beforehand that gives us a sandbox to play around with some concepts of Qt-Quick 3D. And as you can see here, it's basically an empty item with a few properties that I can bind to do a few interesting things with inputs and outputs. So if I show you what the application looks like now, it's just a simple black rect with a little settings panel that I can interact with some sliders, which will change the properties that we have in the sandbox. And you'll see how that'll work. But it basically saves us some time of not having to get into the nitty-gritty details of controls. So being that we're writing QML code here and we want to use Qt-Quick 3D, being that it's not part of the standard Qt-Quick bundle, we have to add an additional include or import. So Qt-Quick 3D, and if we don't want these little squiggly lines in Creator, at least for this version, we need to give it a version. Versions aren't required in Qt 6 anymore. It'll just use the latest version available, but at least the code modeling Creator hasn't been updated for that yet. Okay, so once we have that, we're able to use the additional items that are provided by Qt-Quick 3D, and the only 2D item that's part of Qt-Quick 3D is called View 3D, and this is actually your bridge between 3D and 2D. So if you want to show 3D content in Qt-Quick 2D, you use a View 3D. And so View 3D, if we just, since it's a 2D item, we can anchors.fill parent, and that'll actually give us a Qt-Quick item that supports this. So to do anything with that, you actually need a scene to render. And so because the default item or the default property for View 3D is the scene itself, you can just put what are called spatial items inside of this, and that'll be your scene. So for example, I'll just go ahead and create a very simple scene. Perspective, camera. That gives us a camera because if you want to render stuff from 3D, you need a camera in space. We'll add a light, just a simple directional light, and we'll add a model. And a model is actually the thing that is being rendered. So this is a combination of geometry and material to actually how that's rendered. So to give the geometry, we'll just start with the source, and we'll use one of the built-in items or the built-in primitives for that called just hash cube. And then for the material, we'll just add a principled material here. And this is our metallic roughness material, so we need to set a few things. So base color we'll set to red, and we also need to set default metalness to 0 and roughness to 0 as well. And that should be enough to render. of course, you don't see anything, but that's because we haven't set the position of any of these items. So what's actually happening is that the camera and the directional light and the model are all at 0, 0, 0, or the position 0, 0, 0 in the scene. And that's a problem because the camera's inside of the cube at this point, so it won't render anything. So if we move the camera outside of the cube, we should see us facing directly at the origin point of the scene, and we see well, in this case, a two-dimensional cube. So if we want to actually, prove that it's 3D, we can create a rotation on the cube itself, not the material. So let's go back and just change the Euler. Oh, come on. Euler rotation. Yes, I don't know. I must have spelled it wrong. Of the Y property 230. Yes, and so there you can see that there's actually a three-dimensional cube. And we could also easily use one of the other built-in primitives like sphere and change that cube's geometry to a sphere. So there we have that. And once you have that into the scene, it's fairly easy to, say, bind some of the material properties to the value sliders we actually have. So if we want to change the metalness or the roughness, we can say set it to the value of value 1 slider or value 2 slider. So now if we were to get into our scene, we could change the roughness of the cube. And you can see here that because we actually have a directional light, which also by default is facing down the z-axis. So we're shining a light directly on that cube or the sphere, and we can see how by changing the roughness of the material, we can actually change how the specular highlight is displayed. It's a similar situation with the metalness. Of course, being that there's only one light in the scene, what's going to happen is the diffuse is just going to get darker, and the specular highlight will get more and more like the base color of the item we're actually highlighting. So, but that just shows the basics of like how these scenes are set up. And actually, all of the item types in this 3D space are of class type, the component type node. This is the 3D or the spatial equivalent of a QQuick item. So this empty item here is a 2D item. Well, in 3D, the node is the base class of all spatial content. And so in this case, we're just kind of wrapping things up, and it's going to look exactly the same. In practice, it just becomes a transform node. So we could even, just change the position of, say, the X value to 50. So that'll actually just move everything in the scene 50 to the right. Of course, that makes zero sense because the camera is inside of that. So everything got shifted. So if we do this, yes, there we go. So now it's actually moved 50 units to up the X-axis. Okay, so let's move on to the next thing. Okay, so the next thing we're going to discuss is lighting and the options for lighting scenes in QtQuick 3D. And to demonstrate this, I'm going to actually add an additional model that I created earlier to show this feature off. So just to show what I'm going to import, it's this it's a simple floor and wall model that I created in Blender. So okay, so being that it's already part of the project, I'm just going to add the component. And that is, the first thing is I need to actually position this item. So I'm going to move this down a bit because everything's already at position 0. And I'm going to rotate it by 45 degrees, kind of like how I had in the Blender view. So 45. I'm going to get rid of this 50 offset that we did previously. And then finally, because the directional light is facing a single direction, I need to rotate the light down a bit so that the floor and the wall can both be illuminated, because otherwise just the walls would be illuminated. And I could show that now, that if we did it now, all you would see is the walls. And if we want to also see the floor, I got to rotate the light down. So rotation.x equals -30. So we rotate it down by 30 degrees. Okay, so now you can see the floor. And that gives us a good baseline of like showing the effects of different light types. So now I can add a few additional lights, so-called punctual lights. We already have a directional light. Then we'll add a point light and a spotlight. Okay, so like I was saying before, the directional light, this just has a single direction of like where the light's coming from, and it goes infinitely in that direction. Position doesn't matter. Think of it like the sun. The sun has it's shining in one direction. It's infinitely far away. A point light is like a light bulb that's kind of floating in space, and it has fall off. So if we want to do something interesting with this, we actually have to give it a position. So, because otherwise it would be inside the cube at the origin again. So if we set the position to, let's say 0, 100, 0, so just directly above the origin point. And yes, spotlight we could set to, let's say, just move it roughly to where the camera is. So Z equals 300. Okay, and now if we run this, it should have all three lights in the scene at the same time, which of course you can't really see anything interesting for, just less shadowing behind the light. So what we can do instead is actually attach each of these lights to only be turned on when we hit the checkbox in the settings panel. So we'll say the first light is attached to enabled 1, second light is attached to is enabled 2, and the third one too is enabled 3. And now when we start it up, no light should be visible because all lights will be off, but we can turn them on. Oops, we can turn them on individually using the checkboxes. So that's what a directional light looks like. In this case, just pointing a little bit down, but also facing the same direction as a camera. In this case, there's a point light directly above the sphere. You can see the top of the sphere is lit, everything below it is dark, and then you can kind of see the fall off with the rest of the scene. And then the spotlight, it has a direction and a position and fall off, so you can kind of see the cone of influence here where it's lighting our sphere and the scene behind it in that cone. Okay, so the next thing about these lights that's interesting is that each one of them can specify whether they want to cast shadows or not. So we could say true and true for both of these light types. I don't think the spotlight shadow would be very interesting in this case because it's directly facing the wall and it would be obscured, but we can go ahead and try these two. And so now again, our completely dark scene. And you can see here that now there's a shadow on the floor beneath the sphere. A similar situation with this one. Actually, we might need to rotate the camera down a bit or move the spotlight or the point light a little bit closer to the camera. So let's just try 100 here, so we can get that point light shadow behind us. Yeah, you can see here. It's a bit closer, so you can see it's kind of dark here. But we can actually turn the shadow darkness up here as well. Shadow factor, let's just say 50. That's kind of dark, but we can go for it just to really blow out that shadow. So let's do this again. Yeah, and there you go. You can see, just crazy shadowing now. And it's actually so much shadowing that it's affecting the rest of the scene. So we really overblown that in this case. But okay, so that shows the punctual lights. The next thing that's more interesting is what's called image-based lighting. And for image-based lighting, you need to have not only do you need to have a HDR texture, which I've already have imported into this scene, but you need to set a global setting on your scene. So in the case of View 3D, there's this property called environment that you need to populate with what's called scene environment. And these are settings that affect everything that's rendered by the View 3D. And here, if you set the light probe property to a texture, and then set the source to this light probe texture that we have as part of our project. Now, instead of using the punctual lights that we had in the scene, it's actually using the image itself to light the scene. And here you can see that things look a lot more interesting, a lot more realistic, a lot more like what was, at least seen in Blender. And here we can, again, set the, start changing the, say, roughness property of this sphere. And you can really see that because everything's reflecting off of it when it's completely smooth, like you see that here. Now, when you rough it up, you can really see, the effect of that. And that's a lot more interesting than just having a few, individual lights in the scene, because that's very artificial, whereas this is more like what real life is. So now if I make it metallic, you can actually, it seems metallic instead of very simulated. But okay, that is the basics of how lighting works. So now I'll show a few scene concepts or things you can do with scenes in QtQuake 3D. So the first thing I want to do is make the scene that we're working with a little bit more interactive with a controller for actually moving the camera around. So let me add a import for picking up some of our helpers. And then I'm going to add a component called WASDController. This is also a QtQuake item, or just a Q object to control something in the scene. And it has a property called controlled object. And if we want to control the camera, we need to give the camera a name. So I'll do that now. And now if I set this here, I should be able to use the W, A, S, and D keys to move the camera around the scene. And I can also use the mouse to actually point where the camera's facing. But this actually points out another issue, and that's that the world's really unsettling, that there's, just a black void, whereas the reflections are, showing that we're on, somewhere with a blue sky. So let's fix that as well. And we do this by setting another global property on the scene environment. In this case, it's called background mode, and there is a enum called skybox. Skybox. And so if you have a light probe texture set, the skybox mode will just use the light probe texture as the skybox. So if we do this now, we should have a sky. Yes. So now we actually have, something that more matches the reality of the lighting situation that we're using. So that covers that. Okay. So I mentioned previously that the default property for View 3D is actually the scene, and we went ahead and created the scene inline. But we don't actually have to do that. We can put the scene wherever we want. And so if we were to create an empty node outside of that View 3D and call it scene root, and then copy all of the scene data inside of the View 3D to this scene root, we could then, all of that scene data can live outside of the View 3D, and then if we want to use it, we just have to set import scene root, and that should work exactly the same as previously. Yes. And that might not seem very useful on the, just like that, but what it actually means is that you can reference that scene data from multiple View 3Ds. So if, for example, I were to create another View 3D here, I could use that same import scene root to show that. And first we need to fix the anchoring. So let's just go ahead and set some anchors. Top parent.top. Just have to do some boilerplate to get two on the screen at the same time. Anchors.left, parent.left, and then we set the width to half the width of the screen. Width times 0.5. Okay, so then we can copy that same thing down here and just change a few values to get a split screen view. Let's see, it's this one. Yes, right and right. And what you'll see here will probably be one side lit and one side not, because only one side actually has lights right now. But if we re-add our directional light, and we get rid of this visible property, what you should see is two different views of the same scene. So in this scene, the View 3D has some global properties to actually do image-based lighting and have a skybox, whereas the second View 3D has no scene environment and it's just rendering it with the directional light only. Yeah, in this case, this one's doing both, and this one's doing only one of those things. But the neat thing about this is that because our WASD controller is controlling the camera in one of the scenes, or in the same shared scene, that when I update that property in the shared scene, it's updating it in both. So I can see the same scene rendered twice. Okay, so the next thing that I would like to show is how you can integrate 2D content inside of 3D. So far what I've shown is putting 3D content inside of a QtQuick 2D application. But what if you want to have two-dimensional QtQuick elements inside of 3D? So there are actually two ways to do this. I'll start by just cleaning up the scene a little bit so that we have something to work with. But what I want to show is at any point in your scene, you can just start using two-dimensional items. Like, so for example, if I wanted to add a text box on top of the model that follows the model around, all I have to do is just add the text component, for example, which is a 2D item, a QQuick item. So if I do this, and I need to set a position, and since 2D positions are inversed of, so I need to move, if I want to move it above the model, I need to set a, say, -100. If I do that, that already should be enough to put a text box. Yes, yeah, so there we go. So you can see here in both of our views that there is a text box now created in the world at that position that I specified. You can see it's not centered here, but what we can actually do is anchoring is actually possible. So if I say the horizontal center of this item is, or I think it's what's it, anchors dot horizontal center equals parent dot horizontal center. That should center the text above the sphere. Yeah, so that's what happened. So what's actually happening here is that anytime you use a 2D item inside of a 3D item, what implicitly gets created is this node. So, and this node has a position in the scene that's inherited from its position in the hierarchy, and any offset from that is in QtQuick two-dimensional coordinates. Alternatively, what I could do if I didn't want to, have to deal with the weirdness of the two different coordinate spaces is just set a y value of 100 on the node, and that should do the same thing. Yes. So, okay. And what's nice about this mode is that there is no off-screen surfaces to render this. This is just rendering the QtQuick directly into the 3D engine with the 3D transform. So that means that you get incredibly clear and crisp text, or whatever you're rendering, it's actually rendering directly using QtQuick. We can go ahead and extend this to, say, add a rectangle. So if we want to have like a box that this thing lives in, so let me move this Y one step up, and let's get the automatic indentation here. Let's set a height and width for this guy. So width, we'll say 100. Height, we'll say 25. And we'll set a color of white. And then instead of doing the anchoring here, we can do it in the rectangle. So the rectangle is, and then we can do a fill here. Anchors dot fill parent. Yes. Yes, so that still isn't anchoring the text in the center of the box. But let's see, what are we missing here? Anchors dot, oh, it's center in. Okay, we don't want it to fill. We want to anchors dot center in parent. Yeah, there we go. That should center the text inside of the box. This is just cute quick isms. But yeah, there we go. So now you have a, you know, a 2D item, and of course, yeah, if you go behind it, you're gonna see the text backwards. But yeah, so it's actually rendering the 2D content directly into the 3D scene. If, however, you would rather render directly to a texture first and use that Qt Quick content as a texture source, that's also possible. So I can show that by creating another model. Let's say this time let's do a cube. And let's see, we need a material. Well, first we set the position to, let's say, x equals -100, so it's next to our sphere. Let's add a material for another principal material. And this time, we're going to set a texture on for the base color. Instead of using just a color, we can use a texture. And normally you would just set a source, and that would be an image file. But what we can do instead is we can use source item, and there we can just put whatever QML content we want. So if we want to say width 256, height 256, color blue. And then let's set some text in that as well. Oops. Don't need all this auto-generated. We could say via a texture. And then we'll set the color of the text to white. Now what we should see is that we generate a cube with, yeah, we'll set a few more properties first. Metalness. Set to 0, roughness we'll set to 0 so we get really smooth look. Yeah, so now we have a cube that has QML content in it, and we could just as easily anchor that to the center. Anchors.centerIn, again, parent. That way our text is in the middle of the cube. Yeah, so there you go. You have a cube that source texture is QML, and then that way you could have, like, you know, dynamic content inside of this. So you have some kind of animation or something, and it would show up in that cube. I mean, sure, well, let's just do that, actually. Why not? Let's say property, oh, no, not property, well, like a property animation. Property animation on rotation. So we're gonna rotate the text inside the cube from 0 to 360, duration, let's say 5 seconds, running, true, loops, animation dot infinite. Okay, so that should give us some rotating text inside of our cube. Yeah, and so there you have a dynamic texture on that cube now. Yeah, so that's how you can, two different options for using 2D content inside of 3D. Okay, So one of the details I glossed over earlier was actually importing your own custom assets. So let's show how that's done now. So typically what's done is that assets that you've created in another 3D import tool are, exported to FBX, GLTF, OBJ, something, so one of these interchange formats. And then what we do is actually convert that interchange format into QML and textures and meshes so that you get a component that you can actually just kind of input in your scene like we did here with the Lightbox. And for the asset that I actually imported previously for Lightbox, you can see here, this is what it actually created was, a series of meshes, so floor mesh, wall mesh, and then, a whole hierarchy of models and materials that actually represent that scene. So that's what we have so far. But if you wanted to import your own asset, you have a couple of ways to do that. If you have Design Studio, it's just a matter of dragging and dropping your assets into that tool and it will automatically convert them. But if you don't have Design Studio, it's possible to use a command line tool to actually do this. So I have a few models here, but I'm going to convert this model called SolEV2019.glb. This is a binary GLTF2 file. So if I want to do that, import that into my project, what I have to do is run the balsum command. This is our asset converter or asset conditioning tool. SolEV is the input. The output will be the SolEV folder inside of Sandbox. So Sandbox is the project that we're actually working in here. So Sandbox/SolEV. We run that command, and what this is doing is, converting the project, this GLTF binary, into QML. So now that we've done that, because I'm using QRCs here, I need to actually add those files to our project. So if I just go here, SolEV, add the QML file, and then also need to add the mesh files that it generated. And if there were texture files as well, that would also need to be added to this project. Okay, so now I've added a new folder and component to our project. So now I just need to, since I put it in a folder, I need to import the folder if I want to access it directly. The folder is called SolEV. And also we should probably clean the project up a bit before we get into all that. So I'm going to delete the stuff we did previously. And what I'll do is that I'll just put it into the scene right here. And yeah, so I'm going to set, going to move it down towards the ground. That should be roughly right. And one thing to note, and that I didn't do on import, is that typically in many different asset creation tools, the default unit factor is in centimeters or meters, but at least the defaults for Qt Quick 3D, if you don't change any of the defaults, it's going to assume that centimeters are the default unit. So we actually have to scale up this model by 100. Scale. No, it's just a Qt.vector 3D 100, 100, 100. That way it'll convert this model that's in centimeters to, or in meters to centimeters. So then it won't be really tiny when we actually run it. And also we should probably get rid of the second view 3D. That's not really useful for this demo. So we're just gonna anchors.fill. Anchors.fill parent. Okay, so that should be enough. And because this project I think is probably 50 megabytes, I'll probably speed ahead so that we can see what it actually looks like. Okay, now the project's built and we'll see what it looks like now that it's running. Yeah, so now we have this car imported into the scene. And you can see the reflections already being picked up on the windscreen from the IBL. And if we go back and look at what actually happened, like I said, it is generating a hierarchy of these primitive nodes. So node, model, material, and referencing the mesh files, which are the geometry that represents this imported item. Okay, so now I want to talk about post-processing effects, things you actually apply to the whole scene after the whole scene's been rendered. And we talked a bit about this already with the scene environment and these global properties for what you're actually rendering. I've reconfigured the scene so that we can show the before and after side by side. So when I change things, you'll be able to see the difference on the right versus on the left. So for the left side, let's say we want to add anti-aliasing. So let's say anti-aliasing. Anti-aliasing mode. Let's see, scene environment dot MSAA. So we add MSAA and we'll set the quality as well. Anti-aliasing quality, we'll set that to high. Scene environment dot high. And now if we look at the model, you can see that on the left side, there are less jagged edges. So you can tell in a couple of different places, especially up here, you can see on the edge, there's a clear staircase going on, whereas here it's a lot more smoothed out. So that's one option that you can do as a post-processing effect on the whole scene layer. Next thing is screen space ambient occlusion. So let me just set up a bit of handles here so we can actually play around with what's available. Let's see, distance, yes, value 2. So value 2 slider will do that, and then AO softness, value 3. Okay, so now we can play around with the screen space ambient occlusion settings. If I slide out the slider here, get the thing lined up right here. So let's jack this one all the way up. And yeah, now we're getting some weirdness because of, yeah, but what you can see here is that we are introducing like some shadowing into the contours of the scene. So you can see here along the edge of the wall, now there is some darkness added to kind of show that there's a crease in the scene, and that'll help your scene pop a bit better, make it look a little bit more natural. Okay, so that's screen space ambient occlusion. Also, when you're using IBL and just in general, like everything's rendered as HDR, floating point textures, and so everything needs to be tone mapped. And you actually have control over how the scene is tone mapped, or if it's tone mapped at all. So, for example, I can turn tone mapping off and let you show you what that looks like. And you might want to use like bypass the tone mapping if, for example, you're going to do your own tone mapping in a post-processing effect. So you can see here that like things are a lot more darker, but that's like the raw color values without any mapping to sRGB space. And so yeah, you could do other things from there, or you can set a different tone mapping mode, because the default tone mapping mode is just a linear conversion. But you could, for example, use one of the other built-in tone mapping modes to get a different effect. So here, it's just different cinematic looks to your scene of how it's actually mapped back to sRGB space. Yeah, so that's tone mapping. And finally, post-processing effects are completely customizable in that you can apply a chain of effects that either a combination of the built-in effects we provide, or you can create your own as well using our API. So actually, I need to import the built-in effects library that we ship with Qt Quick 3D. So that's under effects. And here I'm going to add a depth of field blur. Yes, so if I add this, we could add another slider property for the focal distance. So value 4, so this fourth slider, and we'll just give it a range that we want to go into. And here we can actually set like what's in focus in the scene using the depth of field effects. So you can see now everything's kind of blurred out, but if we slide the slider, we can change what's actually in focus. You can see the car's logo is in focus now. Now it's blurred. So that's just, we have a lot of different built-in post-processing effects that you can use and yeah, do interesting effects on your scene. Yep. Okay, so let's talk about some ways that you can customize the engine for your needs. Because so far we've talked about things that are built in, but most people have custom needs when they're doing rendering. So the first thing is that we have a custom material API to allow you to have materials that define behavior in a more programmatic way. So here I've created a small scene that has a couple of custom material types that I've created, and each one shows off how the two different APIs that we have for custom materials, both of which are implementing the custom material component. So the two types are unshaded and shaded. So the first type is unshaded. This is closer to what you'd expect if you were just writing raw OpenGL shader language code. So no lighting stuff is provided. So the actual like details of the scenes, so lights and shadows and things like that, like all of that is on you to actually implement. So I've implemented a custom shader here, just a simple vertex shader, and you can see here you're writing GL shader language, like modern style GL shader language, but we've actually, created a convenience API for actually, exposing built-in properties. So for example, the model view projection matrix here is just, if you use this here, it will, when you actually compiles the code, it'll inject in the correct name for that uniform. And same thing with this position property. So like in this case, like because you're writing GL shader language code, that's going to translate to GL position, that built-in type. But since behind the scenes, it's actually compiling to different shader language types, not just OpenGL. It's kind of nice to have it in a generic way. So here you get nothing. You have to do everything you want. So since I need to know the world normal and the position of the item in the fragment shader, I actually have to specify that here. And because I'm passing things in between shaders, I need to specify, the varying. And then in the fragment shader, I'm just doing a simple Lambert diffuse to get some shaded light. So, and I also have to synthesize a light because like I don't know in this type of shader anything about the lighting in the scene. So any like light things that I've added, it's not going to expose that to that. So this is the completely custom case that I know what I'm doing. Trust me. And you just write your code. So, and you actually have a frag color out here. Again, this is GL frag color if you're familiar with GL shader language. So I'm just saying, okay, do the shading based on the synthesized light direction and output that. So that's one thing. The second thing is that in the actual material, if you've ever used the shader effects in Qt Quick, this pattern will be very familiar to you, that you can just add whatever property you want in QML, and whatever you call it, that's exposed as a uniform in the shader code. So you can see here we have this diffuse color, which is just a QML color, and anywhere in our shader code we can then use that uniform name. So we do that here. So so then you don't have to worry about writing, defining all your uniforms up here at the top. The only thing you really have to worry about is these varyings when you're passing data between different shader stages. So yep. So what you get there is a simple shader that's going to, when applied to the cone, actually give you this thing. And you can see here that it's not actually using the IBL because again, this is an unshaded shader, and so you only get what you output from that frag color, and in this case it's just a Lambert shading. Okay, so the second type that we have here is this, we create another material class that the default one for anytime you implement a custom material is called shaded. And rather than, letting you just do everything here, what this is actually doing is augmenting the built-in principal material type, so our metallic roughness shader. So if you don't give it a vertex shader or a fragment shader, it's just a principal material. So everything's optional, including when you start writing the shaders. Like if you don't set certain properties, we just assume the default that's in principal material. So in this case, I'm only implementing a fragment shader here. So if we go into the fragment shader code, you can see this is quite different. This doesn't look like, GL shader language code because I'm not writing to frag out. Instead, what I'm doing is just changing the built-in properties of principal material. So setting a metalness, a roughness, and a base color. And the base color is actually taking that same, using that same pattern for uniform properties. And the same thing works with other uniforms. Like, so if you want to expose a texture to this shader, you could do that and then sample your texture here. Really, it provides quite a flexible way to create custom materials without having to write loads of code to do, say, support shadowing or IBL. And we have a full API for like customizing how lighting is actually done. So if you want to change the lighting methods in this, there's additional functions for actually saying, oh, well, this is how you should handle directional lights or spotlights, or or the specular term, for example. You could have your own custom way of handling that, and that'll actually use all of the built-in stuff. So all the lights, all the shadows, and the IBL. So you can see here that just by setting those like 3 lines of code, we get for free the IBL support in this custom material that I created, which is just a pink color shader, and that's how that works. Okay, so in a very related thing, or using a very similar API, it's also possible to create custom shader post-processing effects. So I've created one here, or at least I've set up a test scene here. So what I wanted to implement was a simple tone map effect, because like I said before, it's possible to, maybe you want to do something either simpler or more interesting with the tone mapping thing. So for the scene, I've actually turned off tone mapping, and you can see what that looks like here. Load the scene. Okay, so everything looks really dark and weird. But I've actually created a new effect called the simple tone map effect. And this API works pretty similarly to custom materials. The difference is that shade or post-processing effects can have multiple passes. So like maybe you want to render to an intermediate buffer and then do something else, or maybe you want to chain a bunch of effects together as part of one effect for simpler processing. But anyway, so if we go into the simple tone map or frag shader, you can see here it looks very similar to what custom materials look like. Difference being is that there's these built-in input and input UV. This is what is the image from the preceding 2D element in the chain of post-processing effects. What do you want to do with it? And then you output to frag color. That becomes your output. And in this case, I'm just doing simple gamma correction here in this line, and that should get the desired tone map effect. So if we go back to the sandbox, all we have to do to add our effect is, well, on the environment, just effects. That's an array, and you can have either one or more here. Simple tone map effect, and just adding that to that array is enough to have our post-processing effect run, and now it looks back to looking normal again. Okay, and the last feature that I want to show off today is a C++ API, actually. So if you want to create geometry at runtime, so rather than using a static mesh file, it's actually possible to create or define custom geometry or procedural geometry using C++. We have a class called QtQuick 3D Geometry, and with this class, it's actually possible to define geometry on the fly. So here I've made this class called Random Point Cloud that will generate a series of vertex vertex point. So the primitive type is actually point. And I'll just generate whatever the count is, which is defined by the count property that's exposed to QML. It'll generate that many points at a random position between, in this case, 300 or negative 300 and 300. And I'm also using the new style of defining QML types. So it's going to be something called random point cloud. And if we go back to the sandbox file, I just import the define that I set up in the project, and now it's possible to use the random point cloud class. So here, for model, instead of setting a source, what I'm going to set is the geometry property. And with this, it just accepts any type that's of type CuteQuick 3D geometry. So here I've set the count to 300,000, because why not? It'll be one draw call. So now if I run the scene, you'll see that it's now created 300,000 points that show up in the scene as one geometry call that gets shaded with principal material. Yep, so that's it for custom geometry. We also have a very similar class for texture data. So if you want to procedurally generate texture data, so say for example you have a texture type that isn't supported by Qt, and you want to support that, you can use, it's a very similar API to custom geometry called QuteQuick 3D texture data. And there's a similar alternative property in the texture class for using that. But that's it for the custom APIs.
Okay, and that's it. I'd like to thank you again for attending my session, and I hope that you will give QuteQuick 3D a try, especially in Qt 6. That's it. Thanks.